Hi everybody, I hope you all had a good holiday. Welcome back. So today we're doing a pure 1 paper. And the first question is essentially it's just a pure integration question, only 3 marks, nothing too much to worry about. And this is all using the classic separation of variables technique. So that's when you drag all the x's on one side and all the y's on the other side, including the differentials. So we'll write that out as dy, and then I'll just take the dx over to the other side, 6 dx over x squared. And now we're going to integrate these. Whoops, integrate them more nicely. Now, if you remember from previous videos, I sort of explained that there are 2 ways to go about this. Either you can perform an indefinite integral, in which case you account for the fact that you've got a constant, and then you put in what's called the boundary condition, some fact about the places that this curve will go, point on the curve, and you plug it in to find the plus c, the constant. Another way to do it is to put this sort of boundary condition into the integral itself, and that at this point serves as it can serve as one of the boundaries of integration. So I'm going to do that because I find it quicker. But if you prefer to do it the other way, if that makes more sense to you, so the other way you'd be going, so let's do them both. So either you could go, if you integrate this on the left-hand side, you get y, and then on the right-hand side, you get minus 6 on x plus c. And then you plug in 2, 9. 9 is equal to minus 3 plus c, and so on. And the other way to do it is to put in the boundary conditions. And here we have, so the lower boundary for y is 9. And at that point, x is 2, so they're going to match like that. And then we're evolving it to some later time where x is just equal to some x, and y is equal to y of x at that exact x. You can see that they match in a way, like the point that I'm integrating between one point and another point. The first point is 2, 9, and the other one is y, x, some future x and y. So in this case, I will have, so if I integrate, there's just invisible 1 here. If I integrate 1, I get y, and I'm evaluating that between 9 and just y of x. And this is going to be equal to, I take the 6 outside. If I integrate this, I get minus 1 on x. And that's going between 2 and x. So on the left-hand side, this is just y of x minus 9 is equal to minus 6 on x plus 6 on 2. And this is going to be equal to, this is going to give you y of x is equal to minus 6 on x plus 12. And the same way, if you look back up here, c would be equal to 9 plus 3, which is 12. So they give you the exact same answer. I just prefer this way because it's quicker. But if it doesn't make sense to you, then by all means use the plus c method. Okay, so this is binomial expansion. And just remember that there's the only type of expansion you tend to meet in paper 1 is the binomial expansion. That's where you have some bracket to an integer, positive integer power. And if you've got that, you can use the formula in the formula booklet, no problem. If you have something to a non-integer power or not positive power, then you cannot use the binomial expansion. Just be careful, but that tends to only come up in A2, where you have to use the Taylor expansion, which is a technique for more for different exponents and tends to be an infinite series. A binomial expansion will always be a finite series because we know it all the way through. Like we know that there's a finite number of terms. It's just a polynomial. So what they want is the coefficients in front of x squared. Well, if you look at the formula booklet, it's in terms of a and b, where in our case, a is equal to 2x and b is equal to minus 1/2 x to the minus 1. I'm going to write it like this, but you see that that's just equal to minus 1 on 2x. I'm writing it x is minus 1 to make this a bit more obvious. And so the series will run something like a to the 6th plus 6 choose 1, a to the 5th b plus 6 choose 2, a to the 4th b squared plus, and then a few more terms. And you'll see that this term will give us 4 powers of x from a and minus 2 powers of x from b, and that'll give us an x squared term. So the coefficient is going to be 6 choose 2, and then you get 2 to the 4th from a, so that whole thing will be to the power 4, divided by 2 squared coming from b. And if you use the formula, booklet, you'll see that this is like 6 factorial over 2 factorial times 4 factorial times 4, and you can work that out in your calculator. So they're not asking you to write out the entire series, so please don't try doing that. You just have to think for like a few seconds and realize that you only need the terms where the powers of x will cancel in just the right way. So this thing will end up with an x squared after it, and then you can just lift the from there lift the formula you need for the coefficient. Okay, so now they want the coefficient of x squared in this series. Well, it's the same series as before, but multiplied by 1 plus x squared. So there will be 2 terms now that have an x squared in front of them. There will be the one we had before, which comes out when we multiply it by 1, when we multiply through the 1. But there'll also be a term in this expansion which has no powers of x, just a number, and then that one will be multiplied by x squared and will then become an x squared term, if you see what I mean. So what we want this term that we found before, but we also want the second term, and for that we need the constant term. Well, the constant term is the one where the a and b kind of cancel in the right way, that that there is no x factor. So we'll have it'll have to be the a cubed b cubed term. And you see that this will have a 6 choose 3 thing in front of it. So this will be equal to 6 choose 3, and then you'll have 2x cubed over minus 2x cubed. So you'll get minus 6 factorial over 3 factorial times 3 factorial, and you can work that out. And then remember that this is just one of the terms, and this that we found before is the other one, so the full thing is both of them added together. Okay, question 3. So what we want here is just some differentiation and a knowledge about straight lines. So firstly, okay, so we've got some straight line, and we already know the constant, but we don't have the gradient. But we are told something about its slope. We're told that it's tangent to this curve at some point P. So what does it mean if things are tangent? Well, if they're tangent, then that means the gradients are the same. And remember, that doesn't mean that the gradient is of the line is always tangent to the curve, because the curve has a changing gradient. It's changing all the time. The slope is changing, whereas the line just has a single gradient. So obviously, it cannot always be. A line can't be tangent to a curve everywhere, but it is tangent at P. So whatever the gradient of the curve happens to be at P, that is the gradient of the line everywhere. So gradient of the curve, well, we get from differentiation. So we have dy dx, and we just differentiate this, becomes minus 12 over x squared. And we are told that this is equal to m, this at P, so at the point P, this is equal to m. Well, what else do we know? We also know that the line passes through the point P, right? So this is the x coordinate. This is what m is. So let's put that in and say y is equal to minus 12 over x at P squared times x plus 14. And at P, x is equal to x at P. Now, we also know that the line and the curve both pass through P. Like, fundamentally, that's where they meet, so they must both be there. So we can use simultaneous equations. And we can say that at that point, mxp plus 14 is equal to 12 on xp plus 2. And we can rearrange this, and we get mxp squared plus 12xp minus 12 is equal to 0. And we can then, solve for x. So we have that xp is equal to minus 12. The formula, it's on the formula booklet, but it should be carved in your heart. 12 squared plus 4m times 12 all over 2m. And now we know that this thing inside this is called the discriminant, given by the letter delta. The thing inside the square root must be 0 because these things are tangent. Remember that del is equal to 0, tangent, del greater than 0, crossing point, del less than 0, never cross. I.e., there's no real solutions because you're going to get the square root of a negative number. So we know that del must equal to 0. So we can set that 12 squared plus 4m times 12 is equal to 0. And this gives us that m is equal to minus 3. Okay, we're almost there. So now we know that we can plug this back into the equation for xp. And this gives us that xp is equal to 2. Just put that into a calculator. And therefore that yp, and then we can just solve either one of the equations to get what yp is, and that's equal to 8. So p must be equal to 2, 8. There you go. And that's all they require for the question. So what do we do here? We used our knowledge that the gradient of the curve is given by the derivative, that two curves that are tangent at a point have the same gradient at that point, that the equations, the point where the two curves cross satisfies both equations. We use the formula. The formula, that's what everyone just calls it, the formula, even though there are many formulas that exist. And we used our knowledge of the discriminant. That's all there is to it. Okay, bit of geometry now and trigonometry. So here we have, we're given something which is a square. And so we immediately know that this line is also be 10, this one is 5, this little one is 5, and an arc of this circle with such a radius. So firstly, we're asked to find this angle here, which I'm going to call theta. And there's a very easy way to do this straight off, is just to use trigonometry with this triangle and this angle, which I'm going to call phi. So we know that the tan of phi is equal to opposite over adjacent, which is 10 over 5. Therefore, phi is equal to inverse tangent of 2. And then we can look at just this whole bit, and this is obviously, remember we're working in radians now, so this is pi radians, this 180 degrees. So theta must be equal to pi minus 2 inverse tangent of 2. And that'll give you that number of radians. So the next question is asking for the perimeter of the shaded region. So we know that arc from the formula booklet, arc length is equal to r times theta. So, if you have some circle and some angle subtending an arc of it, the length of that arc is r times theta, where theta is in radians. That's very important. If you give theta in degrees, you'll get entirely the wrong answer. In fact, this is the origin of radians. It's all related to this. The fact that there's 2 pi, that the circumference of a circle is 2 pi r, which means that the circumference of a circle is the arc length subtended by a full 2 pi radians. You see? So if my angle is actually like the whole of 2 pi, what I'm subtending is the entire circumference of the circle, and that is 2 pi times r, which is the circumference of any circle. Anyway, so first we want to find r. Well, we can just look again at this triangle here. And we can use Pythagoras to work out the hypotenuse of that triangle. So r is equal to square root of 10 squared plus 5 squared. And you'll see that that's equal to 5 square root 5. And we know theta. So you can get, this gives us the arc length. But that's only half of the problem, because we also need this thing. So the perimeter includes this 10 centimeter bit. So just add 10. So plus 10. And that'll give you 20.4 centimeters, which is the answer. And now, oh, hello, there's another drawing of it. Great, that's very helpful, actually. Okay, find the area of the shaded region. Well, again, we're going to use our knowledge of what the arc length is. So the area of this region is just the area of the whole slice minus the area of this triangle. So the whole slice, this is again from the formula booklet, is 1/2 r squared theta minus 1/2 times base. This is the base that we already said was 10, times height, which is also 10. And we know that this is 1/2 5 square root 5 all squared times the theta that we found before, minus 100 over 2, and that's very easy for you to calculate. So really all of this required is you not to panic, to think about using trigonometry and how the angles will fit together, and to look in the formula booklet for the arc length and sector of a circle equations. Okay. So here we have some pure trigonometry. But it's really only actually requires the use of one, at least the first bit only requires the use of one of those identities which are in the formula booklet. But we'll see how that works. So a squared, well, that's going to be sine squared theta plus 9 cosine theta plus the mixed term times 2, so minus 6. Sorry, not times 2. Oops. Yes. No, it is minus 6 cosine theta, because there's 2 copies, plus b squared, which is 9 sine squared theta plus cosine squared theta plus 2 copies of the mixed term, 6. Oops. This term was sine theta times cosine theta, 6 sine theta cosine theta again. And I tell you that because these cancel happily. And we get 9 sine squared theta plus sine squared theta is 10 sine squared theta. And there's 9 cosine squared theta, whoops, plus cosine squared theta is also 10 cosine squared theta. And this is just equal to 10 because this is equal to 1. And that's the identity that you need to use. So now they, and you can see that this is constant. This is just a number. The theta dependence cancels out, and you just get a number. Now they want you to find the values of theta for which 2a is equal to b. So 2a is 2 sine theta minus 6 cosine theta. And this is equal to 3 sine theta plus cosine theta. and we drag them around, we get that sine theta is equal to minus 7 cosine theta. And there's a couple of ways of doing this, but I think the easiest way is to divide through and get tan theta. So remember that sine over cosine is equal to tan. So tan theta is equal to minus 7. Now, if you plug this into your calculator, you'll get that theta is equal to minus 1.428 radians. But that's not even in the region that we're looking at. If you see, they've said that theta is between 0 and 360. So this is just an artifact of the way calculators calculate answers. But let's draw the tangent function. You'll have to do this. And it looks something like that. And this one comes back up, and then so on. And remember that unlike sine and cosine, the period of the tangent function is only 180 degrees. So it kind of repeats itself each 180, each pi. So that's 2 pi, that's pi. And minus 7 is sort of down here, right? And the value that we were given was here. But we want this value and this value. So we can easily obtain that, right? We know this value that we were given is 1.428 radians away from like below 0. And we know this one is going to be therefore 1.48 radians below pi, and this one 1.48 radians below 2 pi. So these are all the same distance. And from that you can go, theta is equal to pi minus 1.428 or 2 pi minus 1.428. And you can just put those into your calculator and write them down. So this is very important. Sometimes they will give you a clue by saying values with an S, but sometimes they won't. But always check that you've got all of the answers in your in the range that they've given you. So we were given 0 to 360, which is 0 to 2 pi. But it was very obvious from the beginning that our naive calculator answer was not going to be good because it's negative and that's way outside the region. But even if the calculator had given you that one, you would have still had to look for the other one and remember that you need more than one, just however many fit into that region. Okay, question 6. Vectors, my favorite. So we're given our vector OA, which I'm just going to rewrite in the way that I like to write it. It's a column. And OB with these unknown numbers. And we want to know when is OB parallel to OA. Well, for this we know that if V is parallel to W, that's the same thing as V equaling some number times W. So any vector, if it's parallel to another vector, is the same thing as just a scaled version. It could be made smaller, in which case your scaling is fractional. It could even be going in the other direction, in which case your scaling will be negative. But it's just kind of the same vector scaled in some way by a number. So we know that therefore 3pq must be equal to some number times 1 minus 2, 2. And that's obviously, you can see that 3 is equal to k, so k is equal to 3. And therefore p is equal to minus 2 times k, which is minus 6. And q is equal to 2 times k, which is 6. So that's the case where they're parallel. The next question says, okay, they're not parallel, but they're telling us that they are perpendicular. So when they're perpendicular, the angle between them is 90 degrees by definition. And when they're perpendicular, the dot product is 0. That's what I'm writing here. V dot W 0 implies that V is perpendicular to W. So we have the dot product between A, 1 minus 2 and 2. And forget about this K that we found before. That was a different case. Now we're saying that they're perpendicular. Dotted with 3p and then q, which is 2p. And this is equal to 3 minus 2p plus 4p. And this is equal to 0. Well, this obviously gives us that p is equal to minus 3 halves. If this way of writing the dot product confuses you, this is pretty much just so that it comes from the way we multiply like big complicated matrices together, which happens later. It's just a habit, but it's the same. All this means in matrix notation is that I multiply this by this and that by that and that by that. Right? So if you haven't seen this before, I apologize, but this is just how you write it, because you can sort of imagine it as lifting the sky up and sort of rearranging it so it's horizontal and then slamming it down on this guy and multiplying each corresponding number. And that is the way you think of it when you multiply big matrices, by which I mean, these guys. Times another matrix, blah, blah, blah. You do this times that, and this times that, and, so it transfers smoothly to this. But whatever way you prefer to think about it is fine. You won't need to know about matrices. But that's what this notation means when I use it. Okay, third question. Another case now. We're told that now P is 1 and Q is 8. Well, that means that OB is equal to 3, 1, 8. And we want the unit vector in the direction of AB. So let's first find AB. So AB, and if you remember from before, this must be equal to OB minus OA. And why is that? Well, if I imagine that I have, some A and some B, this is not what they actually are, but like just for reference. If I want the vector pointing from A to B, that's the same thing as going from A to 0 and then from 0 to B. Well, from A to 0 is the opposite of going from 0 to A, so this must be minus OA. And going from 0 to B is the same thing as OB. So the full A to B is the same thing as minus OA plus OB, or OB minus OA. So this is equal to 318 minus whatever A was, 1 minus 2, and this is equal to 236. Now, is this a unit vector? Well, it's check. We take the magnitude of AB, and that's just the Pythagoras thing again. So that's 4 plus 9 plus 36. And if you look at the calculator, you see it's 7. So the length of this vector is 7, which is not a unit vector. Unit vector means that the length is equal to 1. Well, how do we change the length of a vector? We just multiply or divide by a number, and that scales it up and down. You just multiply, it becomes longer or it becomes smaller. So all we need to do is divide by 7. So the notation often used is the vector with a hat on top, and that means that that's the unit version, that it's been scaled correctly so that it's equal to the magnitude is equal to 1, and that's going to be 1 on 7, 2, 3, 6. Okay, question 7. We have we're told we have a line here, and there is some point R, which is the reflection of another point. So let's actually draw this just for illustration. You have to find it by calculation, but it is going to be easier to explain if I just draw it. So what does our line look like? Well, I'm going to rewrite this as y is equal to minus 2/3 x plus 11. So you see quickly that the y-intercept is going to be at 11, and the x-intercept is going to be at some positive value here. And so our line looks like so. And then this point, minus 1, 3, is over here. And there is some reflection of it through a line perpendicular to it, and that's R, perpendicular to the other line. So we want, firstly, the equation of this line. So equation of the line. Well, we know that it is perpendicular to the other line, whatever we're calling it, line 1. Therefore, and when two lines are perpendicular, it means that m1, so the gradient of one times the gradient of the other must be equal to -1. So you see that m of our line 2 must be equal to 3/2. And we know that they cross at some point. So the equation of the line currently is y is equal to 3/2 x plus c. And we know that at some crossing point, this is equal to the other line's equation, which is -2/3 x plus 11, because that point there, that crossing point, will satisfy both these equations. And this gives you oh wait, hold on, sorry. We actually, I didn't even need to do this. I've just realized that you can actually use a different point. Forget about this point, much easier to do this. You know that this line passes through that point there. And, this point here, the one we're given. Of course, the line passes through that point because, you know. So y is equal to 3/2 x plus c. And at that point, y is equal to 3, and x is equal to -1. So this means that c must be equal to 9/2. So the equation of line 2 is y is equal to 3/2 x plus 9/2. Great, now we're getting somewhere. Now we can find the crossing point very easily. And at that point, these two equations are the same. So we have 3/2 x plus 9/2 is equal to -2/3 x plus 11. And if you juggle this around, you get that x is equal to 3 and y is equal to 9. So these are the coordinates of that crossing point. Now what do we have? This requires like a little bit of conceptual thinking, but if I want to get from here to here, you can think of that as a vector, as me just adding a vector, which gets me there. Then you can see that adding it again will get me to R. So if I know what vector I've added to get from the original point to the crossing point, I can then just add that vector again to get to R. Well, the vector v is just going to be equal to the crossing point minus, so remember, it's the same thing as going from, let's call this A, and let's call this B. So to get from A to B, this is going to be OB minus OA, which is going to be, OB is just the crossing point coordinates, 9, 3, minus whatever the A was, -1, 3. Yeah. Wait, did I write that the wrong way? Oops, I wrote that the wrong way around. That's 3, 9, apologies. So that's 3 and that's 9. Yeah, that would have been crazy. Okay, so this vector AB is 4, 6. And therefore our point R, well, that's going to be equal to the crossing point, which is 3, 9, plus another copy of that vector, 4, 6, which is 7, 15. Okay, now I hope that was clear to everyone. This was our first task, was to work out this line. And we used the fact that the product of the gradients would be -1, and then we plugged in. So this is plugging in the point -1, 3. And that gave us the equation. And then we found the crossing point. And then we worked out this vector. And that's the technique you should use if you have a reflection of a point in a line. It may seem like really scary at first. Reflecting things in the x-axis and the y-axis is easy because you just reverse the sign of the relative relevant coordinate. But reflecting it in a line requires this technique. There are other techniques, but me, I really like vectors, so vectors seem to be the most straightforward way to get it. Okay, question 8. So we're told the volume of a solid circular cylinder is 250 pi. Well, think about a cylinder. If you don't have the equations memorized, it's pretty easy to work out what the equation is to get the volume. So the volume is going to be equal to the area of this top bit multiplied by the height, because you sort of take the area and then you have like h copies of it almost. You sort of take it all the way through. So the area of the top is pi r squared times h, whereas the surface area, well, that's equal to 2 copies of the area of the caps. So that's 2 pi r squared plus the area of this, whatever this is, the side of it. And that is you can think of it as the circumference of this times the height. Because if you unrolled it, if you cut a slit down the side and unrolled it, you just get a square. And this would be 2 pi r along the sides, and the height would be h. So the surface area just of the sides is 2 pi r h. So we're told that the volume, pi r squared h, is equal to 250 pi. And I'm going to solve this for h. So h is 250 over r. And therefore S is equal to 2 pi r squared plus 2 pi r h, which is 2 pi r squared plus 250 times 2 is 500 pi r over r, r squared. R squared, and that's what you're required to get. So now we need to differentiate. We're asked for the stationary value of s with respect to varying r. So that means you differentiate s. You want to know how s changes with r. Well, that's a derivative. So, right, ds dr, that's going to be equal to 4 pi minus 500 pi over r squared. And this is equal to 0. So at the stationary point, if you evaluate this at the stationary point, you get 0. And we solve for r. And that gives us, so let's see, 4. Oh God, I forgot an r there. Dropping r's all over the place. 4 pi r. So this gives us that 4r cubed is equal to 500. So r is equal to cube root 175, which is 5. And they're asking for the stationary value. So what is s at 5? Well, you put that into your calculator, and you can get the answer pretty quickly. Now they want the nature of the stationary value. So this means the second derivative. So d squared s dr squared is equal to 4 pi plus 2 times 500, which is 1000 pi over r cubed. And if you evaluate at r is equal to 5, you get that this is equal to like 12.6, which is greater than 0. Therefore, this is a minimum. So remember the rules. If d squared y dx squared, if it's greater than 0, this is a minimum. If it's less than 0, it's a maximum. That's just checking the nature. Now, just remember that this stuff here is only true if the first derivative is equal to 0. If the first derivative is not equal to 0, then there's nothing special about that point. I mean, then it doesn't matter what the second derivative is particularly. So you need to check both things if you're asked for minima and maxima. Okay, question 9. So we've got a function, and they want us, first question, just find the derivative, no problem. That's very easy for us. So this, we have to use the chain rule. So you should just practice doing this with, various simplified ones. You can also use the product rule. In fact, the product rule is just a sort of special case of the chain rule, but I always prefer to use the chain rule. So that's if you have f of g of x, if you differentiate this, that's equal to df dg dg dx. So here, f, of some quantity is 5 over a, and g of x is 1 minus 3x. So firstly, dg dx is equal to minus 3, and df dA is equal to minus 5 on a squared. And of course, a is g. So f prime of x is going to be equal to minus 5 over g squared times ddgx, which is minus 3. And that's the correct answer. So there was just a plus there. That should go on the outside. So now they're asking us to determine if f is increasing or decreasing, or neither. So this means that it's, always increasing. Always increasing with x. So it means that as x goes up, f goes up. Well, the easiest way to test this is to test the derivative. Is the derivative always positive, which means that something is going up, or is it always negative, which means it's always going down for any value of x greater than 1 or equal to 1? Remember, that's where our function is defined. So we don't care about values of x, less than 1. We don't care what the behavior of the function is there. All we care about is what its behavior is in this, in its domain. So the question is asking, is the first derivative always positive, always negative, or does it change? In which case it's neither, it's one of the function that goes up and down. Well, we can see that, we've got 15, which is something that is greater than 0. And we've got 1 minus 3x, all squared. So things that are squared are always greater than or equal to 0. If we're talking about real numbers. And in this case, this is actually always greater than 0 because x is always bigger than 1. So the only time that this could be 0 would be if x was equal to a third, but it cannot be. So these are always going to be greater than 0, and this implies that f prime of x is greater than 0 always for any value of x that's allowed. Well, that's great. So that means that f is an increasing function. Now they want the inverse function. So the technique for this is rearrange and then substitute. So I'm going to call my f of x is equal to, so 5 on 1 minus 3x, and I'm going to say this is defined as y, just for ease. If I rearrange this, I get 1 minus 3x is equal to y on 5 on y. And that means that x is equal to, third times 1 minus 5 on y. So this is x in terms of y, but if I now say that my function is f of y, so that x is just equal to some function of y, but I'm going to call this f minus 1 of x. It basically just substitute in x wherever you see y. I mean, x and y are just variables. They're just labels for things that you're giving and taking out. So I could easily call this, f minus 1, g, h. I could give it an x or a y, but the point is it's the inverse function of this guy. So I just have to write it like they want it. So the function, the name of the function is f, or f minus 1, not f of x. But the thing inside the brackets, the x is what I'm giving it, and then it tells me what I do to that if I give it x. The inverse function goes the other way. So it doesn't matter if I say f of y is equal to 1/3 1 minus 5 over y, or f of x, so f to the minus 1 of x is equal to 1/3 1 minus 5 over x. It's the same thing. And they want us to find it. They tell us what they want the label to be called. So there it is. But this is a technique. So set equal to y, rearrange, relabel. If you just want to pass the exam, that just memorize that technique. Don't think about too much the thinking behind it, but really that's all it is. And now they want us to find the domain and range. So we know that the domain of f is equal to the range of f to the minus 1 and vice versa. So the domain of, so I'll write a little domain range of f. Well, the domain was x greater than or equal to 1. Therefore, that's the range of f to the minus 1. Well, it's not x anymore. It's y. But there's a little subtlety here. And the point is that, yes, y must be greater than or equal to 1. Or that it will be, like the output of this function here, this inverse function, will always be greater than or equal to 1. But the range is a little more subtle. So what is the range of f? Well, f, if we give it our minimum possible value of x, we get that we get this as minus 5 on 2. And if we increase x, remember we can't decrease x, so this is our minimum value, increase x, this means that f gets less negative. So it grows, which gels with our thinking earlier, but it never passes 0. It gets this number with a negative after the negative sign gets smaller and smaller, which means it becomes less and less negative. But it will never be greater than 0, because to be greater than 0, this thing on the bottom would have to be positive, and it can't be positive for x greater than 1. So we know that y can get very, very, very small as you make x like enormous, because you're dividing by something that gets bigger and bigger and bigger, but it will never hit 0. So the range of f is y greater than or equal to minus 5 over 2, but always less than 0. We can say that it's sort of less than or equal to, because x could go to infinity, in which case you would get the limit would be 0, but that's an argument. And therefore that is the range, the domain of f to the minus 1 of x, because they're the same. Okay, I hope that's clear. It's a little bit funky to think about, but that's the general procedure. You are given the domain for f, so you know already the range for f to the minus 1, inverse f. But the range can be a little trickier. You have to think about where the limits are, and what possible things you could get out. So the best thing is to work out the actual range for f and then make that equal to the domain for f to the minus 1. Okay, now we're looking at series. So the first one is an arithmetic series. So an arithmetic series is the one of the form a plus k plus a plus 2k plus and so on, where you just each term just increases by the same amount on the previous term. And we're told that the first term is 12, great, and that the last term is 48. So I'm going to say that there's n terms. Therefore, the last term is given by a plus n minus 1 k, and this is equal to 48. So therefore, k is equal to, and we know that a is 12, so subtract that, is equal to 36 on n minus 1. Remember, there has to be minus 1 here. This is very important because this is the first term, and this is the second one. First term has no copies of k, second one has 1 copy of k, third one has 2 copies of k, so it's always minus 1 of what term you're on. So it's a plus n minus 1 copies of k is the nth term. And now we know that the sum of the first 4 terms is 57. So if we look in our formula booklet, we find a formula for the sum of the first 4 terms. And it's going to be 1/2 times 4 times 24 plus 3k. And we're told that this is equal to 57. And if we solve this, we get that k is equal to 3/2. And we already found that this was equal to 36 over n minus 1. And if we solve that, we get that n minus 1 is equal to 24. So n is equal to 25. So that's mostly just applying the formula booklet. Okay, now the next one is a geometric series. And these are slightly different. These are the ones of the form a plus ar plus ar squared plus so on. So each term is just the previous term multiplied by some number r. And we're told that the third term, so that's 1, 2, 3, the third term is 4 times the first term. So we know that ar squared is equal to 4a. And this means that r is equal to plus or minus 2. There's 2 possible values, which is why they say values here with an s. So you have to take both of the values of the square root. And then we're told that the sum of the first 6 terms is k times the first term. So if we use the formula booklet again, we get sum of the first 6 terms is a times 1 minus r to the 6 over 1 minus r. Well, r to the 6th, it doesn't matter if r is plus 2 or minus 2. It's an even power, so the whole thing is going to, like this whole r to the 6 is going to be positive. So it's going to be a 1 minus, and I think it's 64 all over 1 like minus or plus 2. And this is equal to k times a. So k is equal to minus 63 over 1 minus or plus 2. So there's 2 possible values, either k is equal to 63 or k is equal to minus 21. And those are the values that we want, depending on what r was. Okay, question 11. Well, we're given a curve and a line, and we're told that they meet here at B, and that at that point they are perpendicular. So we know that at that point, their gradients are the same. Well, how do we find the gradient of a curve? We differentiate it. So dy dx is, and this you just differentiate a square root, you get 1/2 times 1 over square root of 1 plus 4x. If this seems weird to you, just practice it using the rules a few times. Times whatever's inside using the chain rule, which is 4. So it's 2 on 1 square root 1 plus 4x. And we know that at that point, it's the y-intercept, right? Well, what's the y-intercept of this curve? That's just going to be equal to 1 plus 0, 1. So at the point B, this is equal to 2 over square root 1 plus 0, which is equal to 2. So actually I should write this as just the coordinates 0, comma 1. So the gradient is equal to 2 at that point. Therefore, the gradient of a tangent line would also be equal to 2. Therefore, the gradient of the normal, so the remember that's m1, m2 is equal to minus 1. So the tangent line would have a gradient of 2. So therefore, the normal should have a gradient of minus a half. So we've got y is equal to minus 1/2 x plus c. And we know that this line passes through the line, it passes through the point 0, comma 1. So we have 1 is equal to c. And so the full equation is y is equal to minus 1/2 x plus 1. And that's the answer to the question. Okay, now we want the area of the shaded region. And this is where, you know, all the juicy marks are. But it's actually not that hard. The best thing is to divide it into 2 sections. So this is our first section. Well, we know that the integral is the same thing as the area under a curve. So our area here, it's going to be the integral of 1 plus 4x to the 1/2, which is just that thing there, dx. And I'm just looking at this first area. So I'm integrating from a to 0. And then the next area, well, I'm going to forget about the curve. I'm just going to integrate this this nice straight line. So that's the integral of minus 1/2 x plus 1 dx between 0 and c. Well, what's a? We need to know the x value of a. So ax, that's just the x-intercept of this curve. So that's when y is equal to 0. Therefore, x must be equal to minus 1/4. And what about c? Well, c, the x value of c, because y is obviously 0, is the x value that you get when you set y to 0 for the straight line formula, and that's equal to 2. So our area is equal to the integral of this, and you should this doesn't look like a super simple one, but you've either seen it before, you haven't, where you have to integrate a square root or a fractional power, and it's actually straightforward to do. So just practice a few times on that if you haven't quite got the hang of it yet. But we know this is going to be something of the form 1 plus 4x to the 3/2, because 3/2 would turn to 1/2 when we differentiated it. But then we have to multiply by 2/3 to account for the fact that 3/2 would come down. And then we have to divide by 4 as well to account for the fact that a 4 would come out. And we're integrating this between minus 1/4 and 0. And then we're adding this area, which is, so minus 1/2 x integrated is minus x squared on 4 and plus x. And if you find this a bit doubtful, just convince yourself by differentiating these things inside and seeing that you recover the original thing. And we're doing this between 0 and 2. So this is equal to, and the first bit, that would become 0. This becomes 1/6 because the lower limit would actually vanish. And plus integrate plus minus 1 plus 2. And so if you put this in, it'll all equal to 7/6. And that is the correct answer. So this is just some slightly annoying integration. This square root thing, that's really important. That'll always come up with these things, is integrating some function, some linear polynomial of x inside a square root. And it really isn't that hard. You just have to account for all the factors that will come out and raise the power of the bracket. And there we go. That's all done. Please let me know if you have any questions about this stuff on the boards, and I'll see you next time.